Okay, section 3.2. Okay, 3.2 is introduction to proofs. The rest of chapter 3 is all about proofs. Okay, proving theorems. Okay, theorem. What's a theorem? Okay, a theorem is a statement that can be proven to be true. Okay, an axiom is a statement assumed to be true. A proof is a series of steps each of which follows logically from axioms or previously proven statements whose final step could result in the statement of the theorem being proven. Example 1. Okay, prove the following theorem. Theorem. Okay, every positive integer is less than or equal to its square. Okay, every positive integer is less than or equal to its square. Okay, so if I take a positive integer, say k, and we're saying that it's less than or equal to k squared. Okay. Okay, so let's do a proof. Okay. So we're going to do a direct proof or a paragraph proof, okay, by writing out statements and then reasons that they're true. Okay. So let x, well, not x, let k be an integer. Okay, where k is greater than 0. Okay, since x is an integer, Oh, sorry, K, I'm sorry, K. Since K is an integer, and K is greater than 0, then we could say K is greater than or equal to 1, right? Because the next integer up from 0 is 1. So it could be 0, it could be less than 1. Okay. Okay. Since K is greater than 0, okay, it's positive, we can multiply both sides of K greater than or equal to 1 by K. And it's not going to change the inequality symbol if we do that, right? If I multiply both sides of the equation here by K, I get K times K is greater than or equal to 1 times K. Multiply both sides of the equation by K, of the inequality by K. Okay, to obtain this guy here. Simplifying, we obtain K squared. Come on. Okay, we obtain K squared is greater than or equal to K. Okay. Therefore, therefore, wait for it to write. Give me the red pen. Thank you very much. Well, give me the circle of death.
Professor, you muted.
Sorry about that. Okay, so therefore, every positive integer is less than or equal to its square. Okay. Okay. And then we're gonna put a little square, and we're gonna color it in saying that we have proven what we've wanted to prove. We started with given axioms and statements, and then we have a squared. Okay. Okay, this actually is a symbol, okay, that represents a Latin phrase. It's quod erat demonstrandum. Okay, which just means it has been demonstrated or it has been proven. And sometimes you'll see QED for short. Okay. Again, it's just says, hey, we've proven what we wanted to prove. We set out to prove. Okay. Okay. Theorem. The sum of two positive real integers is strictly greater than the average of the two numbers. Okay. The theorem can be expressed in logic using quantifiers. Okay, so we can express this in logic using quantifiers. For every x and for every y, okay, x greater than 0 and y greater than 0, implies that if we add x plus y, it is greater than, strictly greater than, the average of the two numbers. X plus y over 2. Okay, the statement there is an integer that is equal to its squared can be expressed once again using quantifiers as there exists an x such that x is equal to its square. Okay. Definition. A number n is a perfect square if for n is equal to k squared for some integer k. Okay, first type of proof is called a proof by exhaustion. A proof by exhaustion. First type of proof. Okay. A proof by exhaustion okay, is a proof by which we prove a universal statement by checking every element in the domain of the statement. And computers are really good at these proofs because we could just say, hey, uh, are there any numbers 1 to 1,000,000 that does such and such? And you could easily write a computer code that would check all numbers 1 to 1,000,000. Oh, yeah. Okay, and we would exhaust all of the domain. Okay. There's a famous proof by exhaustion called the four colors theorem that says you can map any map with only four colors. And that was proved, I think, in like 1976 using a computer. And nobody could prove it before because nobody had the muscle power to, you know, go through all of the exhaustive cases that you would have to go through to show that there's no case that doesn't exist where you can't just use four colors to color any map. So it's a very famous proof. Some people didn't want to believe it was proved because it used a computer to prove it. It's outside of the realm of, you know, human beings with just pencil and paper to prove. But they eventually accepted it as a proof by exhaustion, and it was proven. Okay, let's do the following here. Example 2. Okay, prove the following theorem. Okay, theorem. Oh, let me move this over. theorem, if n is an element of -1, 0, 1, then n squared is equal to the absolute value of n. Okay, so what's the proof here? Well, the proof would just be to show that these are true statements for each of these elements in the domain. Proof. Okay. Let n equal -1. Then n squared is equal to -1 squared, which is 1, which is equal to the absolute value of -1. So that checks. Let n equal 0. Then n squared equals 0 squared, which is 0, which is the absolute value of 0, and that checks. And then let n equal +1. Then n squared equals 1 squared equals 1, which is the absolute value of 1, and so that checks as well. So this is a proof by exhaustion. Okay, it has been proven by exhaustion. Okay, so therefore, if n is an element of -1, 0, 1, then n squared is equal to the absolute value. Okay, so I'll move the proven down here after the therefore. Well, maybe I'll state what type of proof it was too. Therefore, by exhaustion. There we go. Okay, for proofs involving universal statements, okay, name an arbitrary object in the domain and we use that statement to begin the proof. Okay. For example, example 3. Okay, begin the proof of the theorem. Let's just begin the proof of the following theorem. Okay, okay, theorem. Every positive integer is less than or equal to its square. Okay. So how would we start the proof? Okay, we would say let x be an integer. Okay, or in our case we used k, I think. Okay. We'll go back to k. Let k be an integer such that k is greater than or equal to 0. Okay, so in the proof that we did, we just said, hey, let K be an integer. Okay, an object in the domain. Okay. So when we're proving universal statements, okay, that for every, just choose a variable that represents an object in that domain. Okay, then go on to the step showing, okay, K is less than or equal to K squared, which we did before. Okay, a counterexample for a conditional statement, like an if-then statement, must satisfy all the hypotheses and then contradicts the conclusion. So all the hypotheses must be true the conclusion, but the conclusion must be false. Example 4. Find a counterexample for the statement. Okay. For any real number, x, okay, if x is greater than or equal to 0 and x is less than 1, then x squared okay, is less than x. So what's the counterexample? Okay, so they're saying if it's between 0 and 1 or it is 0, then it's less than. Well, the counterexample would be 0. Okay, let x equal 0, then x squared equals 0, which is equal to x. Okay, 0 is not less than 0. Therefore, the statement is proven false. Now, it wouldn't be false if we got rid of 0. Okay, it would actually be a true statement. Okay, and then we'd have to actually prove it. But in this case, we can just throw up a counterexample and disprove the statement. Okay, proof type number 2 is a constructive proof of existence. Constructive proof of existence. Okay, constructive proof of existence. A proof that shows that an existential statement to be true okay, by showing an element of the domain has the required properties. Of the domain has the required properties. Okay, so if it's an existential proof, it means it's that there exists, right? So there exists something that does this. So we just have to find the something that does that. And then we're good. Okay. So let's look at this theorem. Okay, theorem. There is an integer that can be written as the sum of the squares of two positive integers in two different ways. Okay, now we there could be more than one. We just need to find one. Okay. So if we want to prove this true, then the proof is going to say, hey, let n equal 50. Okay. We could try all the numbers 1 to 49, they might not work. But if we try 50, I think we get the first value that actually works, because we could say 50 is 1 squared plus 7 squared, which is 50, and 5 squared plus 5 squared, which is 25 plus 25, which is also 50. Okay. Therefore, okay, we just need to show that there exists an integer that has those given properties. The integer 50 can be expressed as the sum of the squares of two positive integers in two different ways. Okay, it's a little harder to disprove an existential statement. Oh, that should be a square there because it's the end of a proof. Okay, disprove an existential statement. We actually have to try everything. Okay, we have to show that it doesn't work for every single item there. Okay, to disprove an existential statement, okay, to show an existential statement is false, one must argue that every single element of the domain does not have the required properties. Right? So it's like a formal proof. For the universal statement, okay, we'd have to prove, show that every one works. For an existential statement, we have to show that everyone doesn't work in order to prove it false. Example 5. Prove the following statement false. Statement. There exists x such that x squared minus x is equal to 1, such that x is an integer. Okay. So we just have to show that no x exists where this would be true. Okay. So if we have x squared minus x equals 1, we could subtract 1 from both sides. X squared minus x minus 1 is equal to 0. And then we could solve for x. Using the quadratic formula, I would get 1/2 minus radical 5/2, or x is equal to 1/2 plus radical 5/2. Okay, and those are the only two solutions for x, and neither solution is an integer, or anything that looks remotely like an integer. Okay, therefore, no element in Z satisfies the statement, and thus the statement is false. Okay. Okay, and that is 3.2.